Is my screen visible?
Yes, sir.
Yeah. Today I'm going to discuss a topic on in analog circuits. I'm going to discuss a topic on MOSFETs. Generally, in the last, if you see previous gate papers from the last 3-4 years, you are seeing a lot of questions on MOSFETs. They are biasing their amplifiers, MOSFET amplifiers, all these things. You're getting a lot of questions in the MOSFET. Nowadays, weightage has increased for MOSFETs because most of the industries are using MOSFETs for the design of ICs instead of BJTs. So there is a lot of use of MOSFET. So most of the questions are in the MOSFET section. In the MOSFET, I'm going to discuss about the enhancement type MOSFET right now. Enhancement type MOSFET. In this we have two types. N-type and P-type. So first of all, what is a MOSFET? MOSFET, it is an active device. Which means it can control the flow of electrons. Examples for this are BJT, MOSFET, etc. And another is the passive device. Passive device, there is no control on the flow of electrons. The device can't control the flow of electrons. Examples for it is resistor, diode, capacitor, etc. I'll explain it in our coming section how MOSFET acts as an active device. And in the MOSFET there are two types. One is I discussed as enhancement type MOSFET, one is depletion type MOSFET. Depletion type. In this, the channel is present initial only. Without any voltage applied, there is a channel present. I will discuss this, what is this channel in depth. Enhancement type. Channel is absent initially. You have to apply voltage to create the channel. I will discuss this in depth. So, first of all, I will discuss construction. Construction of enhancement type MOSFET. Enhancement type MOSFET. So, coming to its construction, So coming to enhancement MOSFET, it has a P substrate wafer. I think so you have idea about P substrate wafer. In this, holes are majority carriers because it has a vacancy in the P type. So it has a holes. This substrate we will take, and we will dope N type in the P substrate. 2 N types. And we will create a contact, metal contact. One is called as source, one is called as drain. You can interchange them because they are symmetrical. Anything can be drain, anything can be source. In the circuit, how I will tell how to differentiate between source and drain. But coming to the construction, anything it is symmetrical. You can interchange them. In the circuit, I will tell how to find the source and drain. And there is an oxide layer between the substrate and a gate contact. This is the gate. So this is the oxide between the gate and the substrate. This is around in angstroms it is. SiO2 oxide around 1000 angstroms kind of thing. This is very thin. This is very thin because gate should control this channel. I'll say what is channel. Here channel is absent initial enhancement type MOSFET. So when the construction is done, it is like this. There is no channel here between source and drain. When there is no channel, in the working I will explain how the channel is formed. And there is one more contact for the body also. This is called body. Substrate is called as body. This is the body. So this is a construction of enhancement type MOSFET. It has source, drain, doped with N type, and the substrate is P sub. Here holes are the majority carriers. Here electrons are the majority carriers in this. And it has 4 contacts: source, gate, drain, and the body. And how this enhancement type MOSFET works, how the channel is formed, etc. I will tell you. Coming to working. Working. So you can see here this is a metal contact, and this also has holes. This also has some resistivity. So when you convert into electrical kind of schematic circuit, so this is a gate and this is a substrate. It acts as a capacitor. Substrate or body. So this is a end of cap and this is another end of the cap. If you apply a voltage here, suppose VGS is applied here, and suppose body is grounded, not grounded, a negative voltage is applied here. If you apply a positive voltage here, the positive ions accumulate, and here negative will accumulate, and here we have an oxide. So this means here the positive ions will be accumulated. So this positive will attract electrons present in this P sub. There will be electrons will be the minority carriers, but still these holes are the majority. It will push holes down, and it will attract electrons up. So electrons will be accumulating here. If VGS crosses a particular voltage called as threshold voltage, this is the threshold voltage, means the amount of VGS required to form channel. So as VGS increases and it reaches the threshold voltage, a channel is formed between source and drain. So now there is a path from drain and source. Before there is no path. This is channel is absent initially. This is what I mean. So until you apply a voltage at gate, there is no channel to the flow of current. Generally, in a N-type MOSFET, current flows from drain to source. So if channel is present, the current flows. If there is no channel, there is no movement of current or electrons. So in this way, channel is formed. If you apply a voltage greater than threshold voltage, the channel is formed. Now, if you apply a voltage between drain and source, now the current will be flowing according to that equation I will discuss. Till now, any doubts are there? Hello? Hello? Any doubts or shall I carry on?
No doubts.
Hello?
No doubts, sir.
Okay. So now condition is, if VGS is greater than VT, then channel is formed. Channel is formed. Suppose if VDS equal to 0, no current flows. Because VD and VS are at the same potential, no current flows. Now, if I start increasing VDS, if I start increasing, current starts to flow. Current starts to flow between drain and source. Because there is a potential difference between drain and source and there is a channel, current starts to flow between drain and source if VDS is greater than 0. Suppose I will again draw that. This is the N type, this is the N type, and this is the substrate. Here you have source, here you have drain. Here you have gate and an outside in between them. And there is a channel here. Yes. Now VDS is greater than 0, current starts to flow between the drain and source. Suppose here I require VG greater than VT for the VGS greater than VT for the formation of a channel. But in practical, you can see that this means that the voltage between gate and the substrate, the voltage between gate and substrate should be, then the substrate will be as the same potential as source, both are ground, right? So voltage between gate and substrate should be greater than VT for the formation of channel. In this case, you can see that VDS is greater than 0. That means if source is 0, VD minus 0 greater than 0, VD greater than 0. The voltage at VD starts on increasing. Some voltage is applied, that is grounded, VD starts on increasing. Suppose in a case that the voltage between gate and the drain, that is at this point, here, at this point, if this VGD is less than VT, because drain is going to increase, source is 0, so here it will be VG minus VS will be greater than VT. Here is side greater than VT, so channel will be there. Now drain is going to increase, so at this edge VGD is less than VT. If suppose VD is going to increase and it reaches a point such that VGD is less than VT, that leads to pinch off. That is nothing but channel starts to pinch off. There won't be any formation of channel because there is no threshold voltage. Threshold voltage between the gate and substrate. So the channel will be pinched off. So this is called as the transistor has reached a saturation point. So if a VDG is less than VT, then transistor has saturated. That is nothing but pinch off. If VDG is greater than VT, channel is uniform. Channel is uniform. Now I will conclude the operation regions. Operation region conditions. First condition is if VGS is less than VT, source is 0, the grounded. If VGS is less than VT, this here we are taking S because in some cases the source cannot be grounded. In that case you have to use these equations, VGS. Otherwise you can directly, here in this case you can directly VG, VD you can use, but in some cases source cannot be grounded. So in these cases you can use this equation. VGS is less than VT, no channel formed. MOSFET is cut off. MOSFET is in cut off region. Now second, suppose if VGS is greater than VT, channel is formed, but in this two cases are there. VDS is less than VGS minus VT. This is nothing but this equation, VDG greater less than VT. Another equation is VDS is greater than VGS is minus VT. In this case, channel is uniform. And it is called as the MOSFET is in triode region. Triode region. Here channel is pinched off. MOSFET is in saturation. These are the three regions of operation of MOSFET. One is cut off if there is no channel, and if channel is there, that is VGS is greater than VT. If VDS is less than VGS minus VT, channel is uniform, MOSFET is in triode region. And if VDS is greater than VGS minus VT, we can say here channel is pinched off. And if you go on increasing the VD, if VDS is equal to VGS minus VT, pinch off happens. If you go on increase, the channel starts decreasing, like it goes decreasing. And at a point, if VD is more larger, then there will be a breakdown. If VD reaches a very high value, there will be a breakdown because channel reaches up to source, then it leads to a breakdown condition. I think so. Till here, there is no doubts. Hello?
Sir, what is the meaning of pinch off?
I'm not able to hear you. Hello? Hello? Can you repeat?
What is the meaning of pinch off, sir?
Pinch off, okay. Yeah, pinch off means you can say here if a VD going on increasing and it reaches a condition such that VDG is less than VT, means there is no voltage difference. There is a voltage difference between VGD less than VT. Then the channel, then there is no channel. It reaches to a pinch off point, like it's nothing but a there is no channel. It reached a point that is called as pinch off point. There is no channel between the gate and drain. It is called as pinch off. Pinch off means the channel is shortened, like kind of thing.
Okay, sir. Sir, it means that in the saturation there is no channel, no means
No,
no
no channel
connection,
between source and drain.
connection. Yes,
Yeah. Yes. No.
even their current flow. There is no contact between these things, drain and the channel. Just clear something.
Yeah, the current flows in saturation region, even though there is no channel, because you can see here it is very small. The length is very small. It is very small. Due to this, high electric fields are developed because electric fields is inversely proportional to length. Channel is very length. This is pinch off region is very small. High electric fields are developed. The electrons are pushed into the drain. So current flows from drain to source. Even though there is a pinch off, there will be a current flow in the circuit due to this high electric fields.
Okay, sir. Thank you.
Understood. So these are the three regions of operation of MOSFET, and how the current behaves in these three regions I will explain. So current in a MOSFET. First one, cutoff region. In the cutoff, VGS is less than VT. No channel. No channel is formed. So independent of VDS, how much VDS you apply, the drain current is zero. Drain current is the current flowing from here. ID. Current flows from drain to source in MOS. So how much VGS how much VDS you apply, the current is zero because there is no channel. In the triode region, condition is VGS is greater than VT, there is a channel formed, and VDS is less than VGS is minus VT. There is no pinch off. Now the current is ID equal to K into VGS minus VT into VDS minus half VDS square. In this you can see that it depends on VDS because there is a channel between source and drain. If you increase this VD, there will be a more flow of electrons. So it is like a directly proportional to VDS, and also VGS has a role because if VGS increases, channel width increases, more current flows. So in this way, this equation, there is a elaborate equation, but this is how, for in the exam point of view, this equation is enough. From this you can say it is directly proportional to VDS and it is directly proportional to VGS, because if you increase VGS, the width increases, more current flows. If you increase VDS, it is nothing but a high voltage, you are driving the resistor kind of thing using a high voltage. So more current flows. This is a triode region. In the saturation, VGS is greater than VT and VDS is greater than VGS minus VT. Pinch off happens, a channel. Here it is called saturation region because the current is saturated with, that is nothing but it is a 2K into VGS minus VTH whole square. Here the current is saturated, that is nothing but it doesn't depend on VDS. How much you increase VDS, the current doesn't depend on VDS. It only depends upon the gate voltage because it decides the width. So it is called a saturation region. The saturation region, this is because if you increase VDS, pinch off point changes. So the overall voltage across it remains this VGS minus VT only. So changing VDS is taken care in the pinch off. It will move backwards, so the voltage across it remains VGS minus VT only. So in the saturation region, VDS has no role. So it is called as a saturated current. It is a constant current. Only depends on VGS. If VDS changes, there is no change in the current. These are the three equations of the current, and K is mobility of electrons into COX. COX is nothing but this oxide cap. Here we have an oxide now. This cap per unit area. This is W by L. This is the width of the MOSFETs, width and length of the MOSFET. Case. And this is VGS is minus V2 also. Generally, K is given, or this equation is individual parameters are given. Most of the cases K directly it's given, so you can directly substitute and check. Now I will say some examples for your better understanding. And okay, symbols. Okay, first. And for a P-type MOSFET, P MOSFET, it is inverse to N MOSFET. You have an N substrate and a P doping and an oxide here. These are the gates. Source, drain, gate. In this, current flows from source to drain. Here we are using current flows from drain to source. In this, current flows from source to drain. Here generally drain is will assume grounded, and substrate body also grounded. And if VSG is less than VT, because gate we have to apply negative voltage here. Negative voltage. If you apply negative N substrate minority carriers, that is nothing but holes are attracted here. Then there is a channel between drain and source. If you apply VSG less than VT, then channel is formed in PMOS. In the same way for a triode region.
I think the equation of
Hello?
saturation is wrong.
Sir? Hello, I didn't get you. This current? I'm not able to hear you. Can you a little bit louder?
Sir, I think ID in saturation region is equals to K by 2 VGS minus VT का square.
VGS minus VT?
Square. Sir, इसमें 2K की जगह K by 2 आएगा. I think so.
K by 2, no, I think so. If we supply VGS minus VT whole square minus half VT square.
Sir, अगर आप triode के region में triode region की equation में VGS
Yeah, understood. Yeah. If you substitute VDS equal to VGS minus VT, it is nothing but VGS minus VT whole square half VT square half VT. Okay. Okay. So, it's K by 2. Yeah, you are right. K by 2. Yeah, that's correct. Yeah, thank you. If VSG is less than VT, channel is formed in the P MOSFET. In the same way, these equations for triode region and saturation region. Here the equations will be reversed. VDS will be changed to VSD. If VSD less than VSG minus VT, it will be triode region. In the same way, VSD greater than VSD minus VT. It is in saturation region of operation. The PMOSFET generally the polarities and the equations reverse. If you do an example, we'll get idea. I'll tell you an example. This is a symbol of N MOSFET. First, I'll tell you symbols. This is a symbol of N-type MOSFET. This is a gate. This is a drain. This is a source. And body generally is generally in N-type MOSFET, body is connected to the lowest potential in the circuit because here there is a diode between like this P and N. There is a diode. If you apply a voltage here, these diodes might be getting on. So that will be a lead to a short circuit path between the ground and the drain current. So generally what people do is body is connected to the lowest potential in the circuit. That might be a ground or something. This is an N-type. And the P-type. This is a source. This is a gate. This drain and body is similar. These are the symbols of MOSFET. Now we will tell you some examples to find the regions of operation. Suppose consider VT equal to 0.4 volts and K let be 300 microampere per volt square. And suppose a transistor is there. At the gate I have applied 0.5 volts and source I have grounded, and at the drain suppose I have applied 0.9 volts. So now how to check its region of operation? So according to our conditions, VGS is less than VT, no channel. So VGS is, gate is 0.5 volts, source is 0 volts, so it is 0.5, which is greater than VT. VGS is greater than VT, so it is not cut off. It may be in triode or saturation. Cut off is eliminated. Now VDS is 0.9, which is greater than VGS minus VT. VGS is minus VT. So 0.9 greater than VGS is 0.5 minus 0.4. So 0.9 greater than 0.2. So this condition is satisfied. So the transistor is in saturation region. Because VDS is greater than VGS is minus VT, so transistor is in saturation. Did you get this example? Now what if we come to the current ID? What is ID? ID we have seen in the equation K by 2 into VGS minus VTH whole square. So ID equal to K by 2 into VGS in saturation region, VGS minus VTH whole square. In saturation. So K is 300 microamps. VGS is 0.5. VTH is 0.4. So 150 into 10 power minus 6 into 0.1 whole square, that is nothing but 1 by 100. 1.5 microamps. So So it is in saturation, so current is 1.5 microamps. Now I will take another example. Find region of operation of MOSFET and its drain current. Under MOSFET, we applied a voltage of suppose you applied a voltage of here 1.4 volts. This is ground, source is ground, and here you applied a 0.9 volts. Now, first condition for cutoff, VGS should be less than VT, but it is 1.4 less than VT is same as previous. VT is 0.4. So this is failing. So transistor is not in cutoff. So it may be in triode or it may be in saturation. Next we will try triode. Triode is nothing but VDS should be less than VGS minus VTH. VDS is 0.9. It's less than VGS is 1.4 minus 0.4. 0.9 less than 1. So this is satisfied. So it is in triode region. Now coming to the drain current. Drain current is this side. Now coming to the drain current, the equation is K into VGS minus VTH into VDS minus half VDS square. This is 300 into 10 power minus 6 Ks. VGS minus VTH is 1.4 minus 1 into VDS is 0.9 minus half into 0.9 whole square. This will be approximately equal to 0.5. So 150 microampere. So this 150 microamps force for this configuration. So this is how you have to find the region of operation of MOSFET and the drain current. Now next we will talk about here. Is there any doubts in these two problems? Okay. First next we will drain characteristics. Now we will see how the drain current varies with VDS for fixed VGS. Now we will see how variation of ID with respect to VDS if my VGS is fixed. Suppose I will assume that my VGS is greater than VT. It has a channel as formed. Now this is my VDS and this is my ID. It will be in milliamps kind of thing. This is in volts VDS. So this kind of configuration we have. So VDS. Initially, if my VDS is 0, no current flows. if my VDS is going to increase, initially it will be in triode region because VDS is slowly increasing. So these conditions will be, initially it will be in triode because VDS is slowly increasing. So it will be less than VGS minus VT. VDS is starting from 0. So it will be first entering into the triode region. In the triode region, you can see that the equation is this in the triode region. For the lower value of VDS, it will be in triode region. If VDS reaches certain value, it reaches to the saturation. In the triode region, you can say that if VDS is very small, it is linear. ID is directly proportional to VDS. If my VDS goes on increasing, this will dominate, and it will like a parabola kind of thing. So if my VDS is small, it will be like a linear kind of thing. Then it will be, if VDS is small, it is more like a parabola kind of thing. And if VDS reaches a certain value known as VGS minus, suppose I'm dealing with VGS1, VGS minus VTH, it reaches a saturation. There the current is constant. This equation. There the current is constant. It doesn't depend on VDS. You can say there is no term of VDS in this equation. So the current is saturated here. So this is for VGS1. So this is the drain characteristics of a MOSFET. As VDS increases up to certain value, current increases. After it reaches VGS1 minus VTS, that is nothing but pinch of voltage or saturated voltage, current becomes constant. Now if I change my VGS, suppose VGS2 and VGS2 greater than VGS1, my current will have a larger slope because it is directly proportional to VGS in the triode and the saturation, and it will increase like this, VGS2. So this will be coming to saturation larger than this because this will be VGS2 minus VTH. My pinch off point changes because VGS2 is greater than VGS. Pinch off happens about VGS2 minus VTH. My pinch off point changes. In the same way, if you VGS3 is there, that is greater than this, like this too. This will be not a linear change, it will be square because in the saturation you can see current is in the square. Here drawing, it will be, gaps will be more. I'm not able to draw it properly. So it will be increasing like this, and it will be like this. It's just the square, because it's directly proportional to square of the VGS. So these gaps will be not a linear, it will be increasing kind of thing. And for VGS less than VT, current will be 0 in this line only. There is no current, ID equal to 0. VGS is less than VT. So this is how a drain current changes. This is VGS. VGS3 minus VTH. This is how a drain current changes with VDS. After VGS reaches pinch off, the current will be saturated. Before that, it will be like a mix of linear and parabola kind of thing. Now transfer characteristics I will discuss. Transfer characteristics is ID versus VGS for fixed VDS. That is nothing but ID in the y-axis and VGS is in the x-axis. So now how the drain current varies, we have to see. We can see that if VGS is less than VT, there will be no drain current. Suppose this is VT. Here my drain current, there won't be any channel formation, my drain current will be 0. As VGS reaches greater than VT, first it will go into saturation because VGS is less. VGS is less, just now started, it reached VT. First it enters into saturation because this condition will be mostly satisfied. Because VGS is very small, VDS just reached VT, so VDS will be almost greater than VGS minus VT. It will first enter into saturation. It will be like a kind of parabola. Then it is slowly, if VGS is small, it enters into triode region, some saturation. But this exact point depends upon the VDS. If VDS is almost near to VGS minus VT, it directly enters into the linear. If you know exact voltage, then we can figure out the areas. And in this, if VDS goes on increases, the channel will be like a, drain current will be like access a short circuit due to that breakdown. So VD up to operatable voltage only, the current will be linear. So this is the current characteristics of the MOSFET. Any doubts still here? Hello? I hope there are no doubts.
No, sir.
Yeah, too. Hello?
No doubt, sir.
Yeah. Now I'll explain the small signal model of the MOSFET.
Hello?
Hello?
Hello, sir.
Yeah.
I am asking, sir, this which current is more in linear or saturation? Which current is more? Will be the more? I think
You can see
saturation
from the,
more.
yeah, you can see from the this graph. This is the saturation current, so it is a maximum. Here it is in the linear. This is less than saturation.
Sir, but in the transfer characteristic, it is looking that you said that is not linear, but it will be more current in the
Here,
transfer characteristic.
here you can see that VGS is increasing, but here VGS is constant.
Yes, sir, but at the VDS value, ID will be more in the linear. In the linear region, you told that.
In the linear region, current will be lesser if the VGS is constant. If VGS is going to change, it depends upon the exact value of VGS. If VGS, here you can see that VGS is initial in saturation, but current is less because VGS is very small. VGS is small in this region. Yeah, here VGS is more, in linear it has more. Here VGS is for a constant VGS, saturation is more.
Okay.
Because in the equation also you can see that it directly depends upon the VGS, both the currents. So for a constant VGS, we can say that in the saturation it will be more.
So why we prefer that enhancement type over the depletion type? Like in industry, we mostly in VLSI we use the enhancement type MOSFET. Like
So
other than
yeah, so if no, I can tell you that because it has no channel initially now. No channel initially. So if my gate is something like a grounded also, there will be no flow of current here. But in a depletion MOSFET, you have to apply some voltage to make the current stopping. This is the enhancement of no channel is there.
So apart from this, is there any other reason or only this one?
And it's I think these current equations are also like you can see that it has a more after it has a proper characteristics. After reaching a VDS, it acts as a constant current source. These characteristics are also important for designing of our amplifiers, etc. One is this, one is a power thing, because it is off all the time, so our current will be less.
Okay, and it means
Power
it ideally it is off, so it dissipates low power. So due to that.
Because there is no channel initially now, so there won't be any flow of current, so there will be a powerless kind of thing, less power dissipate.
Okay.
Hello?
Hello,
Not
sir.
able. Hello?
Hello?
Yeah.
Hello, sir. Can you, sir, explain again, sir, the region, the linear and saturation in the transfer characteristics, sir? Doubt it is still not clear, sir.
Yeah, okay, sure. I will explain with some voltages I will take and explain. If my VT equal to 0.4 volts, and VDS is equal to some 0.6 volts. Now my VGS initially is 0. So it will be in cutoff because VGS is less than VT, so it will be in cutoff. Until VGS is reached VDS, it will be in cutoff, so current will be 0. Now if my VGS is 0.5, that is greater than VT. Now it might be, so it is not in cutoff, it may be in triode or linear region, triode or saturation region, anything it is possible. So now I apply that formula. First one, VDS is less than VGS is minus VT for triode region. Now VDS is 0.6, less than VGS is 0.5, minus VT is 0.4, 0.6 less than 0.2. This condition is not satisfied. So it is in not triode region, it is in saturation region. So first of all, whenever it reaches VT, it enters into the saturation region because of this. Because VDS, it depends upon the voltages what you have given to VDS. Here I'm taking 0.6 volts. So it will be in saturation region. Now we just going to increase. Suppose it reaches a voltage such that it reaches a 1.1 volt. Here it is, suppose it reaches a 1.1 volt. This is 0.4 volt. Saturation. So now my current will be VDS is 1.1. VGS, okay. Sorry. VDS saturation region, the equation is VDS greater than VGS minus VT. Now my VDS is 1.6, VGS is 1.1 minus 0.6 greater than. This is 0.6.7. Okay, VGS is so this condition is not satisfied. So it is in. So after it reaches 1.1, it will be in linear because VDS is less than VGS minus VT. It's in a linear condition. So first initially it enters into the saturation region, then enters into linear generally. But if my VDS is are very low kind of thing, means first directly enters into the linear region. So with this example, I think so you are clear, like why it is entering into saturation first, then into the linear.
Yes, sir. Clear, sir. Thank you, sir. Thank you.
And linear region, it has more current here because here VGS is more, you can say 1.1 above it is there. The saturation it is lesser because it is VGS is small. But in generally, saturation has more current.
Thank you, sir.
Yeah. Now we'll talk about a parameter called as transconductance. Generally, MOSFET is a voltage controlled amplifier. And BJT is a current controlled amplifier. The MOSFET is a voltage controlled amplifier. Voltage controlled amplifier, and the MOSFET output current depends on input voltage. Applied. So it is an active device. It controls the flow of electrons. So if you apply voltage here, VGS, this decides the current flowing through it in saturation region, or in the triode region also. This decides the how much. In the triode region, both this and VDS decides how much current flows. So it is known as an active device. It decides the flow of electrons. Now there is a parameter in for a MOSFET that is nothing but the output current GM, transconductance, output current change with respect to the input voltage, dou VGS. So this is a transconductance parameter for a MOSFET. If there is a change in input voltage, how much output current is changing. So if I assume a saturation region, then the current is K by 2 into VGS minus VTH whole square by dou VGS. That is nothing but K into VGS minus VTH. So this is the transconductance of a MOSFET in saturation region. Means if you apply a voltage across VGS, this much, if you apply small current change, small voltage change, delta VGS, this much current change will be happening at the output. So change in delta ID for a change in delta VGS is this is VGS minus VTH into delta VGS. So this you remember. Generally GM we will calculate in saturation region only, because in triode region it will be less. So GM will be lesser. So we need GM more for amplification. If for a small change there is a lot of change in the current means, we will get a high amplification. So GM in saturated region is preferred than the triode region. So generally we operate MOSFETs in the saturation for high gains, because we can see more currents are there, more gain will be there. So now I'll discuss the small signal model. In that you will be clear of this GM small signal model. So coming to the small signal model of the MOSFET, we have three terminals: gate, drain, source. Here gate and source, it is an open circuit kind of thing, VGS. Because here there is an oxide, no between gate and substrate, no current flows from VGS. So there is no high infinity kind of resistance is there. It's like an open circuit. And between this voltage VGS controls the drain current according to this equation, and this is a GM. So this voltage controls the current from drain, that is nothing but GM, and GM into delta VGS, GM into VGS. The small signal, these are small changes, delta VGS kind of thing. Small changes we will use, because DC will be short circuited in the AC analysis. So we have a small change in delta VGS, GM, here it will be GM delta VGS. And between the drain and source there is a channel, so there will be a resistance between them. This formula is 1 by lambda ID. Lambda will be given in the values like K, lambda, these are all constant that will be given. So this is a small signal model of a MOSFET. So if you suppose if I will discuss a common source amplifier first. Suppose there is a resistance of 100k and this is a drain voltage. Drain voltage we take it as from the example we will take it. This will take 1. Suppose 0.9 was you applied here. This 100k. And you applied 0.5 volts here. Upon this 0.5, if you apply an AC signal, and what is the voltage gain here? It is the output. Now gain is V out by VA. VA is the input here. Now I have to find the gain. So now I will convert into the small signal model. Small signal model, I have to, this DC I have to short, will replace with the internal resistances. That is nothing but short circuit. So VJ apply VA here. This is a gate. And source is also grounded. And I have a GM VGS. And I have a R0. And my drain also, drain have a resistance, and this is grounded because in the small signal model voltage sources are grounded. So I have a resistance 100k and this is grounded. Now I have to find GM. R0 generally it is given and it will be very high in mega ohms kind of thing, so we can neglect 100k parallel with the mega ohms. You can replace it 100k because high resistance with low resistance, it will be parallel if you going consider at 100k. Or if the lambda is given, you can calculate from the equation. So now I have to find the GM. I'm assuming this transistor is in saturation. I will prove it is in saturation with afterwards. First assumption is transistor is in saturation. So now my current will be ID equal to K by 2 into VGS minus VTH whole square. This we have calculated. It will be, so it is 1 second I'll calculate. K from the above equation we know 300 micro by 2. This is VGS is 0.5, VTH is 0.4. K is 300 microampere per whole square. So this is 0.1 whole square. 300, 150 divided 1.5 microamps. So 1.5 microamps is the current flowing through it. So this is the current here, it is 1.5 microamps. Now I assume that transistor is in saturation. Whether it is in saturation or not, we can see here. So the V0 will be 0.9 minus 1.5 into 100k. So it will be 1.5 into 10 power minus 6 into 10 power 5. So 0.9 minus 0.15. It will be 0.75. VDS is greater than VGS minus VT. So it is in saturation. So my assumption is right. This current is right. 1.5 microamps. Now GM, coming to GM, it is K into VGS minus VT. K is 300 into 10 power minus 6. So GM, this is the equation in saturation only. So I have proved the transistor is in saturation first. So now I'm calculating GM for the small signal model. Then 10 power minus 6, VGS minus VT is 0.2. So it is 30 microampere. 30 microampere. So it's current 30 microampere per volt. The unit of it is 30 microampere. Now my small signal model is, this is Vi, this is ground, this is ground. GM is 30 microampere. VGS is VA. This is VA because VA we applied. And we have R0 parallel with 100K and replaced with the 100K because R0 will be very high. So 100K parallel with R0 will be 100K only. This ground is shorted, so it will be 100K. And this is the drain is the V0. This is the V0. Because this is a drain, this is the gate, this is the source. Drain we have V0. Drain, source, gate. So my V0 will be, this current flows from here. So voltage will be developed across here, plus minus. So minus 30 microamps of current flowing into 100 into VA. So V0 by VA equal to minus 30 into 10 power minus 1, it will be 3 for 15 minus 4. So gain equal to V0 by VA equal to minus 3. So this is the gain of this common source amplifier. This is called a common source amplifier because my source is common to both gate and drain. This is grounded. So input is applied at gate and output is taken at drain. So it is called as common source amplifier. So this is the small signal model of the amplifier and a common source amplifier example. Do you have any doubts? Hello?
No, sir.
So this is the brief introduction about enhancement type MOSFET, how it is fabricated, like how it is constructed, and how the regions will be changing with upon the terminal voltages, its operating regions, and how the current varies in each region, and with some examples we discussed to find the regions of operation and the current. And this is the drain characteristics and transfer characteristics of the enhancement type MOSFET. And we also discussed a brief intro to the small signal model of the MOSFETs. What is the common source amplifier and how the gains are calculated, what is the transconductance of it, etc. So remaining things we will discuss in further classes. Yeah. Do you know any doubts are there, or shall I conclude?
Sir, please, sir, use blue pen, sir. Red is not visible much.
Blue pen, huh?
Yes, sir. Instead of red, sir.
Yeah, here background is, that's okay. I will change it, no problem. Yeah. Okay, I will see this. Now it's mixing, you can see here. Okay, I'll see another colors which are more comfortable. I think so, yellow would be better, I think so. Yellow is better, no?
Yes, sir.
Yeah. Okay. I hope there are no doubts. I'm concluding then.